DICOMs are such a pain. Okay. Honestly, they're not that bad. I actually kind of like the way the standard was architected and how it works. I think I bit off more than I should have with this. That's all. Now, if you're a well-adjusted person with a social life, hobbies, and whatnot, you're probably wondering what a DICOM image is. While I'm not sure how I convinced you to come here, I'm very grateful you did. So long story short, DICOM is a file format and communication transfer protocol used at every medical facility in the US and abroad because it's the international standard for handling medical imaging data. DICOM, D-I-C-O-M, stands for Digital Imaging and Communications in Medicine, and evolved from attempts to standardize MRI and CT scan data because originally it was so vendor specific that you couldn't take anything anywhere. So why am I interested in it? Well, I've got this shoulder MRI, and while I could just use the viewer that I was provided by the imaging center, I got it into my head that it would be a fun little side project to distract me from, quite frankly, the contents of that MRI. So, like every good programmer, I started off by ignoring the 300-page publicly available specification and documentation and trying to find a summary of the file format online, only to give up shortly after. I couldn't really find anything that had what I wanted. So I started poking around the actual spec. I mean, it's only 300 pages, right? I've read 800-page datasheets before. Like, this can't be that bad. For starters, it's a binary file, so I have to use the file stream and handle the file pointer and reading in the data myself. Most file types have restrictions on the data in them, like having only ASCII characters, that make them easy to process by software, for example, a text editor. A DICOM byte stream contains a bunch of different types all jumbled together. Given how complicated medical information systems are these days, this is necessary, but it adds a large burden on the parser, which is me. I guess the first thing to do is to find an image to look at. DICOMs are organized into a big file structure by patient, study, series, and then objects, and then in those objects are the actual image files. I just use the file tree to pick one at random and then dump the character byte data to the terminal to look at it. So you can see the file header here. Each file is supposed to start with 128 bytes, followed by the characters DICM. So, I start off by opening the file and then scrolling through each byte until I find the D. Then I check for the ICM, which naturally should always be at byte 128 through 131. So, the main task is to actually pull data from the file. But looking at the raw data, I have no clue what any of this means. I mean, look at my notes, for goodness sake. Like, what is this? What? It turns out there isn't any information encoded into the structure of the data, which is what I mentioned earlier. The data is actually wrapped up into these tag metadata payload structures, and then all of these structures are written sequentially into the byte stream. First, you read the tag, and then that tag is associated with some collection of metadata, as well as a specification for the payload. And this payload data, it can be integer, it can be a character string, it could even be a bit stream in and of itself. So if I want to pull data, first I need to build a library that I can use to look up the tag. Thankfully, they're all in the standard, and there are only 5,000? Well, there's no way that I'm typing this all out by hand. It took a bit to figure out how to make this happen, but it wasn't actually all that bad. First, I went to the HTML implementation of the standard and used Excel to pull the table from that website. Then I concatenated all the values to get just strings, and then I copied those strings into Notepad++, a text file, which I could use regular expressions in to sanitize all the weirdness. Seriously, regex may seem abstruse, but in certain situations, it is a huge lifesaver. Then I wrote a little script to take the sanitized text files and then put all the data into nicely packaged structs that I could copy from the text file output to my element library header file. It's not perfect, but it was easy enough for me to just kind of laze out and call it good. Now that I've got all the data elements, and there are technically a little less than 5,000, I just need to pull all the meta element tags, which use the reserved 0x002 group number. Right. An element tag consists of two values, the group number, which specifies a group of tags, and an element number, which specifies a single element in that group. With this library built, it's pretty easy to write a search function given the group and element numbers read in from the DICOM byte stream. The hard part is to pull them from the file. All the bytes are packed sequentially. It goes group number, element number, value representation, which is basically the data type, value length, and then the value field, aka payload data. Note that all of these are padded to have an even byte length. So in order for me to scan a tag, my function has to 1. Assume that the file pointer is in the right place. 2. Read in 2 bytes each for the group and element numbers into integer variables, and pull the element data from the library. 3. Read in the value representation, which is 2 characters, and compare that against the search values. 4. Read in the value length, which is actually 2 or 4 bytes depending on the value representation. And finally, 5. Read in the payload data to a buffer to be handled on a case-by-case basis. My scanning function actually returns the number of characters. The buffer it fills is passed into it by a pointer. This way, if the payload is longer than the buffer that I've created, multiple reads can be handled separately by the code, and you know how many you need to execute. So it also makes it easy to backtrack the file pointer to where the data starts in the file, which is useful later. And now I can step through file tags. Admire my work. Please, this took so much more effort than I thought it would. In order to actually extract the image data, I need a couple things. One is, obviously, the pixel values. The other is information about how those pixel values are stored in the byte stream. The number of rows and columns, the number of bits allocated for bits per pixel, etc., etc. So first, I decided to pick the low-hanging fruit. I wrote a function that scans through the file for a specific tag, namely the pixel data tag 7FE0001110. Then I wrote a function that does this for all the important metadata values and returns them in a struct containing that data, as well as positioning the file pointer to start reading at the beginning of the pixel data. And you can kind of see the data pulled out here. It's in the terminal. There's nothing else to do but to try looping through each pixel and then writing the value to an image. Then you take that image and you load it as a texture, and then you render that texture. And just how Raylib works. At first, I thought it was a huge failure, but then I noticed if I kind of squinted a little bit or looked at it from an angle, I could just barely see a picture, which means it was only partially a failure. Turns out I had messed up handling the number of bits to use and which ones to discard, which is encoded into the high bit. So 16 bits might be reserved for an image, but only 12 of them are used. I fiddled around with converting the scanned bit values into grayscale, and I got this, which, wait, this is an X-ray. I guess I picked the wrong patient or something. Anyway, the image was flipped and rotated. Turns out I got the rows, columns, and the XY backwards. I also screwed up the file pointer location, which is why this piece of the image's right side is on the left side of the texture. Honestly, I'm super lucky I got an image at all. A much bigger issue is that the colors were inverted. White was black and black was white. I went back and fiddled with the bits for a while, and then fiddled some more, and then spaced out for a bit. Then I just used a linear mapping function to fix it. And now it works. So now I just plugged in the file path to an actual MRI image, and that's not right. Turns out the MRI uses a different pixel allocation, which made my image all wonky, and that needed fixing to properly display both the X-ray and the MRI. Now, at last, I can finally start the fun stuff. There are two things I really wanted to do here. One, I wanted to process the image to extract structured data. And two, I wanted to use the images to generate a 3D model. While I may have had to manage expectations in regards to the feature set and overall polish of the final deliverables, I was gonna get most of the legwork done. So first, I rendered the image texture to a black mesh. Now, one thing about Raylib that's actually caused me a lot of frustration has been the camera. I can never get it to move how I want, and now I have got this bizarre clipping issue. Between this and the weirdness I had with the Kinect and some other stuff, I don't know what's going on, but I won't be able to avoid this forever. I can avoid it now, though. I just fixed the camera in place and resolved to handle all the rotations myself. And as naturally as breathing, I got carried away. I decided to use quaternions. For those of you who don't know, rotations are a tricky thing to represent mathematically, and they pose some problems when programmatically generating graphics. Take a 3D model. A model is some texture stretched over a wireframe, which is just a bunch of triangles connecting a group of vertices. If you want to draw this model in some direction, you have to take each point and you have to move it to its new location in order for it to render. The process of figuring out that new location is applying a rotation transformation to the model, and requires that both the initial state and some representation of the final state be stored mathematically as variables. I'm not exactly qualified to explain this, but I'll try to give a rough overview anyway. Perhaps the easiest method to wrap your head around is a gimbal rotation. If you imagine a 3-axis gimbal with the model in the center, you can rotate the model to point in any direction by sequentially rotating each gimbal. The issue is that sometimes these gimbals line up and you kind of get stuck, which makes the computer freak out. A more complicated method is to use a rotation matrix. You store the direction in a matrix which, when multiplied to a coordinate, represented by a column vector, produces the new location of that point. They have a ton of applications in group theory and applied quantum, but that's a little too far down the linear algebra rabbit hole. Long story short, they're nice in some ways, but they're computationally inconvenient, and honestly, I find them somewhat annoying. The third method to use is quaternions, which are probably the most difficult to understand. Here we go. Let's say an orientation is the end result of applying some series of rotations to an object. It's just the object points in some direction. Any orientation can be achieved by rotating the object by some angle around an arbitrary axis. This is Euler's rotation theorem. It's a convenient way for generating the final net rotation to be rendered, which is how Raylib does it, but it's not great for actually figuring out what that final axis and angle value should be. Quaternions provide a tool for easily tracking successive rotation operations and then generating the axis angle representation that we need. Now, a quaternion is the extension of the complex plane to 3 dimensions. The complex plane is used a lot in electrical engineering and physics when analyzing waves, like a sinusoid, because it's a very convenient way of representing oscillations. We just think of the oscillation as being, a rotation in the orthogonal plane, and when we're analyzing the actual physical phenomena, we discard the imaginary component and we only consider the real component. What's convenient about this representation is that we can progress the quote-unquote oscillation by applying a rotation to the complex value. And to do that, all you do is multiply your point by another complex number of length 1, aka on the unit circle, which represents the angle of rotation. If you multiply by I, you rotate the point 90 degrees. Multiply by I again, another 90 degrees. You multiply it by square root 2 minus square root of 2 times I, you rotate backwards 45 degrees. If you stick to the unit circle, a complex number is both an orientation and a rotation, and you can keep multiplying them together till the cows come home. Quaternions extend this to the realm of 3-dimensional rotations. It's really easy to apply successive rotations, which is good for a user interface like what I want to make. It's also easy to interpolate between 2 orientations, and it's trivial to set a known orientation. The concepts just take some time to get used to. Anyway, I programmed it all myself before realizing Raylib included a quaternion implementation. Oh well. I even made this click-to-drag feature that I'm pretty proud of. If I want to generate an object from the image data, I need to figure out how to extract the object boundaries from the image background, which means I need to identify the outer edge. So the first thing I did was try to average out the Gaussian spikes of different sizes to handle noise, which instead produced this blur effect that turned out to actually be more useful, so I'll take it. I need to find the edges, the places where the color changes from light to dark. Mathematically, the way we quantify this is known as the image gradient, which is a computational extension of the vector calculus's gradient, which is an extension itself of the calculus derivative. Cue math rant number 2. I promise it's the last. To start with, let's take a curve. It can represent position over time, pressure versus temperature, whatever. In basically every field of study, you can get a lot of useful information from how quickly these values change, the curve's steepness, per se. If you're coming from algebra, you'll hear that and think, rise over run, and you're half right. We take this slope calculation, and then we keep shrinking it until the run becomes technically not 0, but functionally it's nil. The rise also shrinks until it's super tiny, so the result of our division is just a normal number. This is what everyone calls the slope at a point, or the rate of change at the point. The line drawn from that point with that slope is the tangent line. Now, if we calculate this value at every single point and then graph those out, we get the derivative. Calculus is just learning how to calculate all these things and applying all the useful properties these values have. When we move to vector calculus, we want to use similar techniques to analyze the behavior of values in higher dimensions. For a 3-dimensional domain, that would be a volume. In 2 dimensions, we are analyzing a surface, and it's honestly not that exciting. In our world, orthogonal things generally don't interfere with each other. Mathematicians will say they're vectors that have an inner product of 0 or something. So what we do is we just divide this surface into a bunch of perpendicular curves. So we have 2 perpendicular curves at that point in question. And we do what we did earlier for each one. Congratulations, you have calculated the partial derivatives at that point. The gradient is all of these values put together as a matrix or in vector form, using the standard basis unit vectors of the field we're operating in. We can calculate the amount of greatest change using Euclid 147, and we can calculate the direction using a trig function. So how does this help me? Well, we then take these concepts and then we extend them to the computational realm. We could visualize an image as a pixelated surface with the height at each point determined by how light or dark that pixel is. Then the magnitude of the gradient at each point will correspond to how much the color changes, which is the edge I'm looking for. Once I've got that, I can just scroll a bunch of points in radially until I hit the image and boom, I've got edge vertices. Now, how do I calculate the gradient of this pixelated image, or the image gradient, you ask? I'm going to use a Sobel filter. Well, filters. There are two, one for the x direction and one for the y direction. These are examples of a convolutional kernel, a matrix which, for each pixel, you take all the pixels around it and you multiply each one by the corresponding kernel element and then just add those values together. You do this for every pixel and you get a new array or a new image with various properties. The Gaussian blur I generated earlier is another example of a convolutional kernel. It's pretty straightforward, and I put the horizontal edges into the red channel and the vertical edges into the blue, and to be honest, it looks pretty uninteresting. But if I generate a grayscale image using the magnitude of both vectors, we get something much more interesting. So I played around with my edge detection using this image for a while, and it's okay. I'd like to eventually add in a bunch of feature detection stuff, and the algorithm I came up with here is just way too basic. Side note, I thought I had actually induced a buffer overflow, but it turns out I just made a mistake checking bounds in a different part of the program. See, I'm a good programmer. So here's all 64 images in the object getting loaded and analyzed for edges. Now all that's left is to take the edge vertices from all the images and generate a 3D mesh and a model from them. This is pretty straightforward, and a lot of OpenGL or computer graphics guys have made great videos on the subject. I just declare a bunch of memory for the vertices, the normals, and the texture map coordinates, and then populate it with the information from the edge detection. Since the MRI takes images at evenly spaced slices, I can just kind of stack the data like a data sandwich. There may be some errors, but look, it's a pretty model. And the texture stuff was actually trickier. UV unwrapping in Blender was tricky enough, and here I have to do it all by hand, in a cave, with a box of scraps! The thing is, you need to generate a custom texture with all the image data, or you get this. Doing this for the top and bottom are easy. I can just copy the MRI picture to the appropriate location in the destination mesh or image. For the edges, I actually interpolated between each boundary point I generated to pull pixel values from the associated DICOM image. Then I extrapolated between the pixel values for all the pixels between the layers to kind of guess what the edges should look like. This means I should be able to slice the model any which way, carving off whatever I want, and still get meaningful surface texturing. That is, if I implemented those features, which I didn't. I wanted to, but just getting here took so long. I'm done. I technically did what I set out to do. The rest can wait till next time. I can't sit here anymore. I've got to get some fresh air. I'm out.